So first, let's recap what we learned yesterday. Is that in D equals 2, that conformal transformation is really just any holomorphic. So if you send Z to some function of Z that doesn't depend on Z bar, it's automatically a conformal transformation. And then you have an algebra of the form of this guy. And you have the other set, and then you have the condition they don't talk to each other. And then we also see that some of transformations are more special. So this is known as the local group, conformal group. And you can also do some transformation that is valid everywhere globally. Well, namely 0 and infinity. And you discover it of this form in some very extensive way with condition that this is 1. And you have it divided by a Z2 symmetry. And what you discovered is this group is a special linear in 2 dimensions with complex number divided by the double cover, which is equivalent to the conformal group you would have found if you just assume D is anything, and then you take D equals 2. So, sorry, I'm slightly confused. Suddenly the number of students increased by like 50%. Okay, so we have a local conformal transformation, local group, global transformation, global group. And then next we say, oh, remember the VIP players are called the primary field. And either tomorrow or on Thursday we'll see why they are so important. But what really we need today is to recall that this thing at a new point, so I'll just be happily only caring about the Carroll part. A Carroll primary field would transform like this, and it is scaled using the new notation with a conformal weight with a holomorphic conformal weight H respect to the original point. Okay, you have seen this last week when you were in general dimension, and this is just how it looks like in 2 dimensions. And then, of course, you have a lot of information about this guy. You can calculate all the correlations functions are determined in some sense. Well, you have some conformal data, but we'll come back to those correlation functions in the last lecture. And they say why we claim that they actually are determined. And you can solve everything and all that. But what you have seen yesterday in the tutorial is an important fact, is that normally you think the energy momentum tensor should be a 2x2 matrix. So, well, it's symmetric, so they should have 3 entries. And naively, I couldn't really expect that they only depend on Z and not Z bar, except because we have conformal symmetry. What you have shown is that the traceless condition get rid of the TZZ bar component, and the energy momentum conservation tells us TZZ is only a function of Z, or in other words, the partial bar of this guy vanish, and the partial of TZ bar Z bar vanish. Okay. So that's with some factor of 2 pi and also a minus sign that you can check out the big orange or yellow book depending on when you buy it. The different Chesko book. You realize there's a normalization factor that would matter later, but his definition is that this is defined to be minus 2 pi times t zz. And similarly for the other one. Okay, so that shouldn't be a surprise. We've seen together in the class and in the tutorial. What we also seen yesterday is that suppose I have a cylinder. Which is described by x0 going this direction, and x1 being the periodic direction. This guy can be mapped onto the complex plane. Okay, but before I go into more detail about the tutorial problem that you have all already seen, let's have some motivation about this. Well, why do I care about a cylinder? Well, suppose you care about a string theory. You take a closed string, let it propagate in time, you get a cylinder. Okay, well, there are always people you know who not care about string theory. And so we have another motivation is that you must have done a lot of this integral, and I'm sure Dan has a lot of assignments, asks you to do momentum integrals. And then the claim is that normally the integral comes with something k to some power which comes from the propagators. So you have something running in the loop, you want to integrate over it, and then you have some momentum on the bottom, and then that has a propagator on the bottom, and you want to evaluate it in this integral. And then you run into trouble if d is large. Then this integral might diverge, which is known as the UV divergence. And then you have some dark magic of getting rid of the divergence, or sweep them under the carpet and such things. Well, string theory claim they resolve this because you have two strings. And if you draw two strings interact and they become one string, it looks like a pair of pants. You can't really identify, hey, they interacted at that one point. There's always some, you can't get too close to each other, so you can't get too big a momentum. That you will get the detail about that in the string theory course. But there is also something called IR divergence when momentum is very small. As you see, if momentum is very small, especially we leave in d equals 2, we might have an IR divergence problem. And then string theory says, look, we solve everything. If you compactify your dimension to a circle, your momentum can't be too small either, because momentum is quantized now. You have the smallest momentum. So you safely says, okay, very good. If you put things on a cylinder, it's great. We don't have a divergence problem. But cylinders are not that easy to study. So we're going to see one way to derive the Virasoro algebra today. And then you can also try to do that thing on a cylinder, which is much more complicated. That will defer it to the string theory part as well. But okay, suppose we're interested in the cylinder. What you have seen yesterday is that if you just take the cylinder and tie this end up and squash it down, which can be formally expressed as a conformal transformation, but you manage to map this onto the complex plane. It's really just stepping on the cone. And then, well, okay, to be technically correct, you map to the complex plane without the origin, because the cylinder has, two holes. It's like a sphere with two holes, and the complex plane will have a one hole at the infinity. Okay. Nevertheless, I believe yesterday what you have seen is that I quietly leave myself in the Euclidean space. But what you have seen is if this is some equal times, so there's a closed string propagated here, and then it gets mapped onto a circle. Like a circle centered at the origin. So this is that guy. And then, if you say the string propagates to the future, it gets to map to a bigger circle. And what you realize, this is called time. On the complex plane, this is called the radius direction. And then furthermore, one important fact will be important next lecture is that you manage to map minus infinity in the infinite past into the origin. Okay. As you have taken many quantum field theory class, a large number of them, you might have heard of things called time ordering. So whenever I'm interested in some correlation functions of some fields, then we want them to be time ordered. And you might have heard about the path integral explanation is that Feynman says if you go from one point to the other point, you want to integrate all paths, and you can just insert a screen in the middle. Says you have to reach the first screen and then reach to the next screen. And then you just discretize all your space-time, and then you realize everything got to be time ordered. Okay, and then now time ordering, since time is radius, so what do we care on the complex plane is the radial order. We still care about it. Okay, so far, this is what we have seen so far. Okay? No questions? And today, since we live on the complex plane, so integral become very important. Which is Cauchy integral. You must have done some of them. It says you do some integral, then you pick up the pole. If you do, 1/z, you pick up the simple pole, and etc., etc. Okay, there is a interesting notation. It's like h bar is h over 2 pi. This d bar z is just equals to dz over 2 pi I. Otherwise, I have to write the 2 pi really a lot of times. And I can't keep track of it. Okay, just make your formula look nicer. Okay, so that integral we'll have to use a large number of times today. So as I promised, we're going to learn this Virasoro algebra today. I have no idea what this algebra has done, that the people name it the Virasoro algebra. I think it's a pretty happy thing to look at. Well, it depends on how do you derive it. Maybe some of them are really painful. Anyway, so we have derived a lot of algebra together, especially with doing the group theory too. So we must have seen a lot of times. So if I say, find me an algebra, your first reaction should be, okay, let me find the generators. And then let me do the commutator. The process might be painful, but the steps are clear. Okay, so for the generators, today we're going to use what we did in group theory, Group theory says if I have a symmetry and say that when you do such a transformation, it will have effect on our operator of field. And this effect infinitesimally is captured by some generating acting on the operator. And then, you might have seen the exponential form, so this is the infinitesimal form. So if you have a finite transformation, then you just exponential it. You do it like a large n number of times and chop it down to infinitesimal, then you get something e to the I alpha theta if you're talking about a U1. Right? So it's always coming with some infinitesimal parameters, and then you wonder how the generator's acting on phi, and then that's just how much the phi will change. So that's how we're going to find our generators. And then we're going to try to find the commutators. So commutator has the following property. Commutator is actually this algebra. Lie algebra has the following property. The first property is it's a binary operator. The rest are irrelevant. Okay, irrelevant. But for my argument, why the next step is important, we only care that it's a binary operator means that you start with two operators and it's get mapped to 1. So the first step, we're going to look at something called the commutator-operator product relationship. It's a very interesting thing. On the complex plane, the equal time or equal radius commutators is equivalent to study the operator product. So we're going to see that very soon, because we want to talk about the radial ordering. You have to get things ordered to do everything else. So after that, you have an operator product. So it's if you have been taking the first week's class, it shouldn't surprise you that we're going to use OPE to fuse these two operators together to become one operator. So we can take 2 steps to do this binary map. First, we get rid of this commutator thing, and it says it's just an operator product. And then we use OPE to fuse them together, and we'll get a 1 operator. Okay, makes sense? And after that, we can come back to actually calculate the commutator and find this algebra. Okay, so that's the roadmap of today. Clear? So first, let's start with radial ordering. As I said, we should get things ordered before we move on. Okay, so the following definition shouldn't surprise you at all. You must have seen this in QFT, that I want to know what do I mean by radial ordering 2 things. Well, you say, I would love to put the guy that happened last first. So if Z is in the outsider circle, then W, then I put this guy in front, otherwise I switch. Okay? Nothing fancy. Okay, now, so that's just a radial ordering. And now we're going to be interested in a mathematics fun fact, or some curiosity lead us to ask such a question. Well, this fun fact will be very useful later. But the fun fact is, which mathematicians are very interested in this, it says, suppose I have an operator here, and I have an operator here. And the question I want to ask is, what if I bring it to do a circle and come back? Well, if nothing changes, then it will be trivial. But if it changes, it's known as a monodromy, which is what mathematicians are interested to know. And the monodromy, in a very common sense, is if you go to the water slide and you're doing circles, it just says you're moving in a circle and you didn't go back to your original place. And in our sense, we reflect as doing a contour integral and the result is non-zero. Okay, so this is interesting to know. So we're trying to do an integral when z is a circle around W. And then we ask this question, what this thing is. Okay, in order to do this contour integral, okay, when I do anything, we should remember they are radially ordered. Because we're interested in correlation function, the correlation function automatically radial ordered. So it's always radial ordered. But if now I want to do this integral, I'm running into some sort of trouble because z and w seems to be changing their ordering from time to time as I follow my contour. So I meant to draw a circle. Right. Assume this thing is a circle at W. So what we could do is that we can deform a contour somehow. Says that we could do integral here. Ha. And then do integral there. And then, since we can take this, so we're taking some contour very close to this original contour and just fill the rest part by a circle. And whenever we're interested in what happens when two operators are close, we always imagine if there is, other things, they are very far away, so there are no poles. And since contour integral really only cares about some insertions, I can deform my contour however I wish. So what I'm claiming is this contour, let's give it a name C, is equals to C2 minus C1. So I could do C2 and do C1 backwards and do the last part of little C1. Okay? So what I want to do is along contour C2, and along contour C2, the reason I do this is along contour C2, since it's completely outside the orange thing, so the radial order is clear. Z is bigger than W. And on the other contour C1, it's also clear W is always bigger than Z. In the mod sense. Okay. So now I can do the Euro trick is to take them to be really close. So the next step is take a limit such that epsilon goes to 0, and we make the C2 contour really, really close to C1 contour. When epsilon is going to 0, those contour actually goes so close, they basically become this orange circle. Okay? So this is the limit I'm taking. If I take those two operators to be ridiculously close together, there's no difference between the green contour and the blue contour. They are the same contour. They're both the orange contour. And so this guy just become integrating over the orange contour. And now we can write them together, which we recognize as a commutator. And it's actually equal time, because now Z and W are both on the orange contour. Interesting fun fact. We just shown that the commutator, equal time commutator or equal radial commutator, can be written as a contour integral, can be written as the product of operators. You just have to keep track where your contour is. So we accomplished step 2.8, I guess. Is the commutator indeed can be replaced by operator product. Okay, so let's leave this fun fact there and then start to look for generators. Okay, so generators. Remember, what I want to say is that the delta phi is equals to something which generates the change in phi. So, following this idea, basically we want to find the delta phi. David promised me that you have seen this. Says if we have a symmetry, delta phi can be written as a commutator of the conserved charge with the phi. And then if you forget this, you either check your classical mechanics note, or you can check the note today in the appendix that shows why this is true. But I assume you have seen this. Okay. And then let's see what kind of charge we want to study. First of all, let me emphasize again, CFT is a thing that doesn't have an action, doesn't have to have an action. We only know it's some physical theory, has some fields, but the thing we know for sure is it has an energy momentum tensor. And energy momentum tensor is conserved, and you must have also think this to recall the charge is something, if I write it in 2 dimension, it's the integral over space of the first, the time component of the current, and the current is something that is conserved. And the argument for this is that we can always use the divergence theorem says that we'll push everything to the boundary, and normally what you do is you push the boundary at infinity, and the claim everything vanishes there. Except that this argument really works on a cylinder, because our space is a circle. It doesn't even have a boundary. So boundary term, well, if you don't have a boundary, then the boundary term definitely vanish. So if you got a current that is conserved, you definitely have a charge with it. Okay, so what we have, remember, is this guy. This guy, if you want to make it in a current, you normally contract it with our Killing vector. And then you have seen last week that this guy is indeed a conserved. Since that's the only thing we know about the theory, which is the energy momentum tensor, which comes from the space-time symmetry, and we can build a current in it, And since we are still studying the conformal group, the algebra of the conformal group, except we want to upgrade it into quantum sense. Before we just use geometry, now we want to actually have a theory, which comes with a conserved energy momentum tensor. So I hope it's not, you can do the exercise changing your coordinate and that such, but I find that it's not very enlightening, so I'm going to take a leap of faith and tell you that the result of going from there, combining with this, going to the complex coordinate will result in this. As Killing vector energy momentum tensor integrated over the space. Makes sense, and that minus sign is coming from when I mentioned that there is this normalization factor to make some word identities groups. Okay. And also there is the anti-holomorphic part, of which I never bothered to write down, and I just hope that they work. So this is the chart we're going to use to find our variation of our operator. Okay. So the next thing to do is I'm just plugging it in. This is remember. Okay. And now we see a commutator inside the contour integral by the fun fact we just learned 5 minutes ago. I can replace it by an integral that is time ordered. My sign is lost. Right? Okay. While the contour is changed, and we could carefully track that, but let's just say that there is some contour specified here. Now it's become contour C prime. But what we have seen is that the commutator can be replaced by just the product of the operator. Okay? And the next step is, well, let's try to be simple, make our life simple. It's a good thing to do in life. And take only one of these guys. Remember that our Killing vector is literally everything that is holomorphic. So I can do a Laurent expansion, and now I'm just taking one of them. It's just making my life easier. Nothing fancy. Okay, now I want to compare this to what I have here. Sure. This should define that with minus 17. Okay. I want this to equals minus an some generator, which for the energy momentum tensor somehow it's called L. And then I really want this to happen. Because our goal is to calculate the change in the operator and call that, from that, extract the generator. Okay? And this will happen if Tz, we expand Tz in the following way. So if Tz has a Laurent expansion, which I don't see why not. Then we can plug this expansion into that counter integral. Okay, maybe let me use another letter, m. And then you realize from Cauchy integral, it will pick up the term when m equals n, which there's a single pole, and then Ln will be picked up. Right? So we realize the generator we are seeking after of the conformal group is really just some wrong expansion coefficient of the chiral field Tz. That's the moral of the story. That's why, I have to go through this. Otherwise, we're like, we have an interesting expansion exponent. Or I could as well write this guy also as a counter integral of z to the m plus 1. You just plug this guy back in, the same argument when there's a simple pole, it'll get picked up. Okay? And now, we get our generators. They are, not surprisingly, related to our energy momentum tensor, which is conserved because of our symmetry. And now, we should really charge ahead to calculate this guy, which is the goal of the today, known as the algebra of the generators. Before that, remember, what we accomplished so far is that if I really charge forward to do this, what I can safely say is I can get rid of the commutator, but I still have an operator product to deal with. In order to map that onto a single operator, I need to OP. Okay, so since you guys have already seen OP, I'll just say it very quickly. The idea of OPE is there's O1 and Z1, O2 and Z2. And then there are some other irrelevant things. They are far away in a sense. You can draw a circle, put a Z1, Z2 inside, everything else is out. And then the idea of OPE is I can replace this guy by a tower of all sorts of operators sitting at Z2 with some coefficients. Some coefficients that is not an operator anymore. It might still depend on Z1 minus Z2 and such. But let me ignore that. Okay, and then more dots. And then the intuition is also very clear that the things cut close to each other. From far away, they seem like one. Say if you make me take off my glasses, I can see all of you guys are like one. Okay. So this is the idea of OP. And now our goal would be, let's calculate some operator product expansion. And interestingly, still without knowing what's the underlying theory. Okay, we don't really have an underlying theory. And I want to calculate the operator product expansion. What is available? Well, we have our primary field. We have our energy momentum tensor. So, an interesting question to ask, what would happen if I brought them together? Well, you should know what happened if I brought two primary fields together. That's a correlator you already get. So the next thing interesting would be bring the chiral field Tz close to a primary field with conformal weight H. And you wonder, what is this? Okay. Normally you write OPE with a curly sign. That just means for OPE purpose, we only care about a singular curve. And we throw anything that is finite and regular. Because remember, these 2 points are supposed to be very close. So those are infinitely larger than the rest of the term. Also, you only care about in a contour integral. So only pose matters. Okay? So how do we do that? We do that by realize, wait, I need to show up here, right? So if I somehow can find another expression of this guy, I will be able to find OPE. So the trick we use to find this guy is called 35 mass equals to 35. So if we somehow manage to calculate that two ways, then equal them each other, and one way is this way, and the other way hopefully gives me something else. I can just compare my results and then read off what this thing should be. Okay. Well, there is also a third way that defines our generator. So we really say, let's try to figure out how primary field transform under conformal transformation. And this, it shouldn't be a surprise. We have seen it. We know exactly how primary field transform. That's how we define it. We define the things transform this nicely, like this nicely. I meant if phi tilde at fz is given by partial f2 minus h phi z, we call it a primary. Right? So let's do this and try to find what's the infinitesimal version, which is define the new field at the same location, subtract the old field. Right? I want to calculate what's the change in the operator. It doesn't make sense if they're not at the same location. Okay, so let me just expand this guy in the infinitesimal sense. So first, I'll just write it down as taking fz equals z plus some infinitesimal things. And so this guy would be 1 plus partial epsilon to the minus h by z. Okay? And this is called the Taylor expansion. I'm going to expand around this point, so I'm going to get partial epsilon times partial phi. And z. Okay, and the other side I get 1 minus h partial epsilon. It's just a first order expansion. And then since this one is already at epsilon, I can just erase this. I only keep the linear term, so whatever the difference is the second order, I don't care. So now I can read off 35 is minus epsilon partial phi minus h partial epsilon phi. Okay. The only thing you do is do some linear expansion on both sides, and then you read off what's the difference. Okay. Now what I do? Now what we do is that, how do I do this? This number is here, so it's probably better to do this one. Oh.
Take it down.
Take it down.
And now.
And now. Right there. Apparently it doesn't commute.
Yeah.
Okay. Very good. Non-commuting geometry of the blackboard could be some research topic. Okay. What I have over there is that I realized that infinitesimal transformation of the primary field is always this. Okay. Well, if I really want to equal these two guys, they are equal, but if I really want to read off the OPE, in the sense that I should actually rewrite this as a contour integral. Okay. So what we do is, I'll just write out the RP. They are all at the W. All these guys are at W. Okay. So if we look at this guy, this guy seems to be fine. I have phi at W already. This guy is problematic. I want it to be somewhere else at Z, for example. So I'm going to write this as the counter integral of epsilon Z over Z minus W. And this guy is just tagging along for the right. Okay, that's just application of this one n equals 1. Ignore this. This guy just moves over there. The only thing I'm doing is that epsilon W is the residue of this integral. Okay. Then we do this again for the other guy. And now we realize, now what I'm interested in is partial epsilon. So this guy would need a double pole. And again, the phi is just tagging along. I missed the picture, right? Some index using of the Cauchy integral reveal these guys. So now I can compare. Because now they all share a minus sign, the integral, and some epsilon z. So whatever I read off from the rest must be the OPE I'm looking for. And we were left with is a simple pole with partial phi on top, and a double pole with h phi on top, and who knows what else. Regular terms, we don't care. Okay, so that's pretty good. From knowing nothing about the theory, but knowing there exists a primary field, we can already write down the OPE. Then sometimes people actually just use this to define a primary field. Say, I have no idea how primary field will transform under a symmetry, but I can do some measurements to see how it behaves with the correlation function of TZ. So they do some measurements, they realize, in the singular behavior is like this. The first term is like this, the second term comes with an H, and then there's no other poles. Then we call this a primary field. Okay. So this is actually a very important and a sort of longish derivation. So we'll tell you a very random thing. The question is, so what do you learn from, see, now you have learned quantum field theory from Dan, and learned the conformal field theory from me. So what you conclude is, Dan tells you none of the infinities matters. You can sweep them under the curves. And now I tell you none of the finite terms matters. You can sweep it under the curve. If you combine them, all your calculation equals 0, because you throw everything away. Okay. So that's our first important OPE. And the next thing to do was, the last thing we can do without knowing further about the theory is you wonder what happens if you bring Z, TZ, and TW together. It's a quasi-primary. It turns out that it's these two terms we just calculated still exist. You still have a simple pole like this. You still have a double pole like this, and the coefficient is 2. remember energy momentum tensor needs to be integrated over the space, so space-time. So it's conformal with is2, and it doesn't have the anti-holomorphic bar, so it must be 2, 0. Okay. So you can write on this term, but then there's some underscored things do matter, and there's some regular terms with the ruler. And the question is, what else comes out of it? So you can make some educated guess. First of all, let's talk about the Bose symmetry. So if you switch Z and the W, it shouldn't matter. That will kill you the third pole. It happened to not kill this because you can do some expansion and then realize this term actually does agree with the Bose symmetry. And then the next term will be the quadrat, the pole, the force pole. And this pole happens to exist and come with a coefficient of C/2. And then you know there's no further, because you're bringing a field with conformal with 2 and another field with conformal with 2 together. So the smallest singular pole is 4. So it's done. And then a lot of interesting thing about conformal field theory is to figure out what the C number is, which you have heard a lot about it last week. This is known as the central charge of the CFT. As you have seen, since all the theory has the rest part the same, so the central charge actually tells you which conformal field theory we're actually studying. And this also controls the conformal anomaly, which you will see it again in Davide's course. And then also it gives you the flow, indication of the flow of the conformal field theory. If you flow from UV to IR, and this is the indicator that monatomic decrease. And then, even more importantly, well, the other importance is that actually next 2 lectures we're going to use symmetry to constrain this C number even more. And what we discover is in D equals 2, some mathematicians finish all the infinite steps and give you a complete list of the model called the minimum models of a bunch of C's that come with a certain number of primary fields. So all the 2D CFT that are minimal has been listed. So they're characterized by C.
And can you repeat again why Z minus omega to the minus 4 is the lowest pole?
Because you are bringing 2 operator that is conformal with 2. So if you think about the conformal transformation of that, again, it transforms as Z 1 over Z2.
Okay.
So if you bring 2 of those together, you can expect you get Z 1 over Z4. Okay, you can just study all the theory and find all the singular parts and find the dual ending. Okay, so for the last 6 minutes, I'll try to do this commutator as I promised, which is slightly long, and I might get lost. So let's try. Okay, now we can finally do this. And we'll find the algebra. Okay, so this guy is first, let's replace it by the definition of this guy, which is TZ, and another contour integral, let's call it dW, dW. Okay, and the next step is pull the integral out. For some reason later will be clear, I'll decide to do the Z integral first. Since I'm not a mathematician, I'll just do the easy one first and then assume they commute. And now, remember that what I can do is I have a commutator of TZW. I can replace that by the operator product, and we can replace that by the operator product expansion. So that's where this chunk comes in. I'm going to write in the reverse order, just because the first two, well, they are pretty easy to figure out what they are. They're just a bunch of counter integrals. Okay, so now we just have to do 2 counter integrals and be happy with our life. Okay, the first step is this crazy quadruple pole, but that just means I have to take 3 derivatives on this guy. And come with 1/3 factorial, which is 6. So it's c/12. And then it has n+1, n minus 1. And then z to the n minus 2. But after I do the integral, it becomes double. Okay. So that's 1 counter integral. And the next guy would be doing 1 derivative on this guy, so it's a2 n+1 c to the n tw. And the next one is the easiest, is a simple pole, so it's w to the n+1 partial t w. Okay, now we just need to finish integral again. Oh, maybe there's another 4. Oh, there it is. Oh, interesting. At least it's symmetric. Okay. So bear with me with this counter integral. And now we can pull all these guys ahead in expansion numbers. And the integral of that guy vanishes unless n plus m equals 0, right? You just want a simple pole out of this. So if n plus m is 0, it's a simple pole. And then the next term is that n plus, well, the next term, let me keep the counter integral. So it's integral dw and w to the n plus 1 dw. Okay, let's leave this guy alone. And for the other guy, let's integral by parts, because I want the partial t is no use of me. I want a counter integral of t, so it will give me back the generator. So let's integral by parts and get n plus 2, and then again integral of dw wn plus n plus 1. Because I did a derivative on it. And then now again it's dw. But this guy is nothing but the L m plus 1, so we get all this crazy thing. All this term. And this part equals n minus m. L n plus m. Which you shouldn't be very surprised, because we have this before. The only difference is now there is this part related to central charge. So we have this before. That's why it's called L. It's related to the weight algebra. And notice some fun fact. If n equals -1, 1, 0, if it's global symmetry, then there is no central charge term. So the global conformal group is not modified quantum mechanically. It's only all the rest of the infinite tower is modified.
Sorry, can you say that again?
So if you look at this term,
Yeah.
if you take n equals 0 or 1 or minus 1, is discrete.
Okay.
So which means for the global symmetry, which is L1, L minus 1, L0, and the counterpartners, it's not a modified quantum mechanics. But it is indeed modified for all the rest of them by exactly characterized by exactly one number, which is the central charge, which describes the which CFT you are studying. So this is the celebrated Virasoro algebra. And we're done today. And tomorrow, since we have the algebra, let's find the representation of this guy. It's not that interesting. So we'll build a Hilbert space and says, look, have primary field and all their descendants. And they will go in form of representation and all the cool stuff. And then the last lecture is the really cool stuff. Is when we realize, look, there's some miracle happens that in very special cases, we can get rid of some parts of the representation and then find out, because you have an infinite number of constraints. And the constraints are so much. You start with a HC plane, so C is the central charge, H is the focal point. And you constrain it infinitely. So the thing you're left with is the zero set. So you're only literally left with some dots. So it's only H and a C are all constrained to be very specific. Before you thought the whole plane is available. But in the end, we have a infinite but a countable number of things.